different methods of resolution. What is resolution? Separation of a racemic mixture into individual enantiomers. Okay, separation of a racemic mixture. Now I will just give you, now see here. This is what is a resolution. One second, somebody is coming. No. So this is what is a resolution. Resolution means separation of DL mixture. Separation of DL mixture into D and L enantiomer. Okay, so this is what is called resolution. Now, resolution have got different methods. Number one, mechanical separation, which I told you, it is hand picking method. Mechanical separation or hand picking. I will use that word, even though you cannot use your hand. Hand picking. Hand picking method. I told you what where it is applied. Louis Pasteur's method. Invention of optical activity is based on this particular phenomenon, this particular method. The second method is biochemical method, in which one of the enantiomer is consumed, destroyed by the microorganism, so that one enantiomer is left behind. But here you have a lot of disadvantage. You should get the right microorganism, and secondly, 50% of the material is lost. If it is ideal, 50% is lost. So that is not these two are not very good methods. You cannot apply it on a large scale. But the most important method which is applied on a large scale for resolution is chemical method. So what you do is you take a racemic mixture, react with an optically active compound, convert it into a diastereomeric mixture. Convert into diastereomers, separate by physical methods, separate them by crystallization. Separate them by crystallization. Now individually convert.
Sir, sound korravana.
Yeah, okay. I will talk louder. I think that is the maximum voice which I have got in my this one. Okay, I will talk it louder. Are you able to hear now? Is it better now? Or it's still very low?
Better.
Let me see. Let me see my one second. Let me just try. Oh, mine is maximum. I kept the whole volume complete, full volume. Okay, just try. So, what I was telling you is take the racemic mixture, react with an optically active compound, convert into diastereomers, separate the diastereomers by crystallization. Okay, now convert each diastereomer each diastereomer back into enantiomers. Back into enantiomers. Convert them back into enantiomers. Okay. So now what is the why do you do this? Why you have to convert racemic mixture into diastereomer? Because enantiomers have no difference in solubility. Enantiomers have same solubility. Same solubility. But diastereomers have different solubility. So that you can crystallize them. So one component can be crystallized out. One component can be crystallized out. Now let us take an example for that. The example, best example, one of the good example which I shall discuss here is you think about lactic acid, DL lactic acid. DL lactic acid. Remember, it is a mixture. One is D, the other is L. Now this is an acid. You react this with an optically active base. Example, brucine. Brucine is an optically active base. So I will use, and suppose we are taking brucine is having L configuration. It is levorotatory. So we are taking L brucine. LB stand for L brucine. So here you have D lactic acid and L lactic acid. Now, this will form two salts. Which are they? L lactic acid, D lactic acid. L brucine salt. And second one, L lactic acid. L brucine salt. L lactic acid, L brucine salt. Now look carefully here. This is a salt. A salt does have a positive component and a negative component, a positive ion and a negative ion. Here the positive ion is the lactic acid COO minus. CH3 CHOH COO minus. CH3 COO CHOH COO minus. The D form of it. and minus salt and brucine plus. Remember, brucine plus. Okay. And see, brucine is having an L configuration. Now you have the L lactic acid. And brucine salt. This is also L. Now see here, this is D, this is L. So this side of the molecule are non-superimposable mirror image. But this side of the molecule are identical. That is what you have to understand. See, this is a salt. The salt is having two parts. Remember, this is a single compound. They are not two compounds. It's a single compound, out of which one carbon is enantiomeric, the other carbon is identical. That means overall the molecule is diastereomeric mixture. Diastereomeric mixture. Okay, it's a diastereomeric mixture, and they differ in their solubility. This salt and this salt, they differ in their solubility. So they differ in their solubility. So what do you do? Crystallize them. So crystallize. One enantiomer will separate. One diastereomer will separate as crystal. One will separate. One will separate as crystal in the crystalline form. Which one? Having the one which is having low solubility. The one which is having low solubility will crystallize out, which separate in crystals. Into crystal. Okay. And the other will remain in solution. Now filter this. Okay. Filter this. So you separate one of them. D lactic acid, L brucine salt is separated. Okay. So during the filtration, you will get mother liquor, the filtrate. This is the residue, crystals. You take the mother liquor. Mother liquor means filtrate. You take the filtrate and now you concentrate this solution. concentrate the solution, and again crystallize it. Again crystallize. You will get the other component. Which one? L lactic acid, L base. This salt you can get. So you have done the separation. See here. Here you have crystallized. Again crystallized means you are getting this salt separated. Filter. Okay, so what you have separated is the diastereomers of lactic acid. Now you have to convert this back into lactic acid. You treat with HCl, any mineral acid. This and this separately you treat with HCl. Separately you treat them with HCl. Your L-lactic acid will separate out. Sorry, D-lactic acid. Sorry, here it is. L-lactic acid will separate. And here also, when you treat, this will liberate your D-lactic acid. So this is how the resolution is made using a chemical method. I just explained to you again. The DL mixture is an equal mixture of plus and minus enantiomers of lactic acid. This is treated with a base. L-brucine, this is a natural product. This a natural product. A natural base, I will use that word. Why you had to use base? Why you had to use some natural product? Because you require something which is optically active. Your base should be optically active, and nature only supplies you best optically active compound. Okay. Now that is so your lactic acid is treated with L-brucine. You get a mixture of two salts. One is D-lactic acid, L-brucine salt, and second is L-lactic acid, L-brucine salt. Now here on one side there are mirror images non-superimposable, but on the other side they are identical. So they are non-mirror images. Stereoisomers which are non-mirror images. So you call them as diastereomeric, and diastereomers have different solubility. One salt will be having more solubility than the other one. So you crystallize it. The one which is having low solubility will separate out. Filter it. The crystal is taken and treated with HCl, you will get L-lactic acid. The mother liquor, the filtrate is taken, it is concentrated and allowed to crystallize again. It will be rich in the L-lactic acid. Okay, so this is basically the chemical method of resolution. Now the fourth method is called selective adsorption method. Selective adsorption method. Okay, this is done using column chromatography. This is done using column chromatography. Column chromatography. You must have studied the principle of column chromatography before. I think you must have studied the principle. It is based on differential adsorption. Different rate of adsorption. Different rate of adsorption. Adsorption. Different rates of adsorption for the enantiomers. For enantiomers on an optically active uh, optically active adsorbent. On an optically active adsorbent. Optically active adsorbent. Examples of optically active adsorbents are starch, cellulose, starch, cellulose, or quartz. Or quartz. So these are the optically active adsorbents. Now, different adsorbent, that is your D and L enantiomer will be moving in the column at different rate, and they can be collected in separate test tubes or vessels. Okay, so this is now the method. This method can be applied for racemic camphor. Camphor, CAMPHORE. So you can use this method for separation of racemic camphor using D-lactose, using D-lactose as the adsorbent. D-lactose as the adsorbent. Okay, so these are the different methods of resolution. So we have covered 4 methods: mechanical separation, biochemical separation, chemical method, and selective adsorption method. Okay. Now let us look at the configuration of these compounds. How will you name them? Say, for example, see here. Let us consider lactic acid itself. Now this is one lactic acid. OH. Here the H is black side. Let us give the name of this compound. 1, 2, 3. It is methane, ethane, propane, propionic acid. Which propionic acid? It is alpha, beta hydroxy propionic acid or 2-hydroxy propionic acid. Two hydroxypropionic acid. This also is 2-hydroxypropionic acid. Two hydroxypropionic acid. Both are 2-hydroxypropionic acid. Then how will you differentiate between them? The method is, one is a relative configuration. First method is relative configuration. Finding out the relative of when is not. The internet is very slow, so it is writing very slowly. Relative configuration. So first one is relative configuration. Now here you can see here is a compound which we have already seen. This is a naturally occurring glyceraldehyde obtained from nature, and this is having a positive rotation. So plus glyceraldehyde. Okay. So it is plus glyceraldehyde. It's having a positive rotation. You have done it by experimental method. You have taken the naturally occurring glyceraldehyde into the laboratory and found the optical activity. Okay. And what people do, they wrote the Fischer projection of this compound in this fashion. See, this is the most oxidized group on the top. You write the most oxidized group on the top. Most oxidized group. How do you know whether it is most oxidized or not? Number of oxygen should be more, number of hydrogen should be less. That's all. So most oxidized group is on the top. So this is CHO group. Now you have CHOH. And now you have CH2OH. See that, it's very easy to understand. So you have to arrange this molecule into a Fischer projection in this fashion. Most oxidized group on the top, least oxidized group at the bottom. See here, this is top to bottom. So CHO comes first, CHOH comes next, and CH2OH comes third. Okay. Now once they have written this structure, it was assumed. Look, it is assumed that the naturally occurring glyceraldehyde is having the hydrogen on the left side, OH on the right side. And they designated this as capital D. Okay. Now what is the meaning of capital D? This is the meaning of capital D. H here, OH here. On the chiral carbon. So the one which is the enantiomer of this will be having this structure one side. Let me wipe out this stuff. Internet is very slow, so my things are working very slowly. That's okay. Now the enantiomer of this will be having the LCHO CH2OH, CHO with enantiomer this. This they designated as capital L. And of course, this will be having a negative rotation. That is doubtless. So the enantiomer of this is called L minus glyceraldehyde. And remember, glyceraldehyde is a standard taken as a reference sample. Glyceraldehyde is a reference to which you are relating other compounds. So what you do is, if a chiral carbon, H and OH or the functional groups are on different direction. If the H is on one side, OH is on the other side, on the right hand side, you call it as D, and here you call it as L. Now suppose you are given a compound. To see whether D, capital D or capital L, you are given a compound. Suppose glucose. Glucose. Draw the Fischer projection of glucose. Here is glucose. 1, 2, 3, 4. CHO here. H, OH. OH. H. H. OH. And CH2OH. Okay. H and OH. Now see here. Now you have to compare. You have to compare this configuration with the above one. Now you have so many H and OH. That is the greatest problem here. So what is taken is, you compare only those carbon which is just above the least oxidized group. Okay. So CH2OH, next carbon is HOH with H on the